All right, last lesson on redox. Now what this lesson is going to allow us to do is kind of cross over to different subjects. Like this first equation is going to cross us over between redox chemistry and thermodynamics. And this will also allow us to calculate a little bit later, not this equation, but a little bit later, non-standard conditions. So first of all, let's remember what we said in yesterday's lesson, that if your E cell, is positive, then that means your reaction is spontaneous. Well, we also learned back in thermodynamics, if your delta G is negative, then the reaction is spontaneous. So a negative delta G and a positive E cell both mean spontaneous. Okay, that's going to be helpful in what we're going to be calculating, because as you can see in this equation allows you to use the E cell to calculate delta G, or the delta G to calculate the E cell. Okay, both of them work. So for the delta G, we want our unit to be in joules per mole. So just make sure, double check that it's in joules per mole, not kilojoules per mole. N is going to represent how many electrons are being transferred. You know how when we wrote our half reactions, we'd have electrons on both sides and they would ultimately cancel, and we had to make sure that the number of electrons was the same on both sides? Well, this represents that number. So if you had 6 electrons on one side and 6 electrons on the other to cancel them both out, then 6 would be your value of N. Okay, we'll practice that in just a second. Then you have your standard EMF, your E cell, and again, that's calculated by doing the reduced minus the oxidized, cathode minus anode. And then this last part is the new part, and this is called Faraday's constant. Faraday was a scientist that did a lot of work in redox chemistry. We will mostly be using this version of his constant, 96,500 joules per volt per mole. You'll notice this one says coulombs per mole. A coulomb is the same thing as a joules per volt. And those of you that are in physics have probably heard that before, or at least AP physics have heard that before. So that's the way the equation works. Just be careful of your units. You're going to have to do your half reactions to figure out what N is and to figure out what your E cell is. I will show you, if you look at the first example problem here, notice how little information there is. Seems like there's not enough to calculate this, but as you'll see, there's plenty of information as long as we have that balanced equation. Now we know that ultimately we're calculating delta G. So I know I'm going to have to use this equation. So you always want to write down what equation you're using right off the bat so that you're thinking about it, thinking about what you have. Now in the problem, they really didn't give us anything. We know that we're solving for delta G. I don't know what N is yet. I always know that F is 96,500, so I'll just write that in. And I also don't know the E cell yet. So I have some work I have to do. But these two missing things can both be found using what we learned how to do yesterday, which was write your half reactions and calculate the E cell using the reduction potential table. So what we're going to do, this equation right here, you notice has already been balanced for you, but when they balanced it, they canceled out the electrons like we always do. And we need to see those electrons. We need to be able to see how many we actually had. So we are going to unbalance it. We're going to pull the two half reactions apart. You can either start from ground zero and do it all, or I would just take what they've already told you. For example, you know that 4Ag and then 4Ag plus are going to be one of the half reactions. So they had canceled their electrons out. We know that originally in the half reaction there had to have been 4 electrons on that side to deal with that plus 4 from the silver. For the other one, it was O2 and 4 H pluses making 2 H2Os. All right. And again, there must have been 4 electrons on this side to balance out that plus 4 that's coming from those hydrogens. So you can see right away it was 4 electrons that were transferred. So that is N. So I get to plug 4 in. So you just figure out your electrons, and the number of electrons you have is what goes there. Then we have our 96,500, and then we need the standard cell potential. To be able to figure out the standard cell potential, we're going to look up both of these values, reduction potentials, off the table. So if you look at the reduction potential for silver, it is listed as 0.8 volts. And the reduction potential for water, find the water one. Don't look at the H plus turning to H2, because that's not what we have in this one. You find the water, it's 1.25 2.3 volts. Okay. Now, there's a couple of ways to decide which one to subtract. You could look at the reduction potential values. You know, the bigger one's the more likely one to be reduced because this reaction was spontaneous. And we could tell that because, oh, actually, well, it has to be spontaneous. They wouldn't be giving it to us in this type of problem if it wasn't. But the other way, the easier way, I think, you've already got the equations here. You see here that these 4 electrons are lost in this first equation. So this must be the one being oxidized. Okay, and then on this one, the electrons are being gained. So this must be the one being reduced. And we know that E cell is the one being reduced. So the reduction potential of the one being reduced minus the reduction potential of the one being oxidized. So the E cell standard is going to be 1.23 minus 0.8. So the E cell is going to be equal to 0.43 volts. Now notice it's a positive E cell value, and therefore since it is a positive E cell value, you know that you are dealing with a spontaneous reaction, and so that's, you know that delta G will ultimately be negative. So now I can come over and plug in my 0.43 here, and my delta G, if I multiply all of those times each other, will end up being negative, which is what we expected, 1.7 times 10 to the negative 5th, and again, delta G will always come out to be joules per mole. Okay, the electrons canceled out the volts part of Faraday's constant. So that is how those types of problems work. Again, look how minimal of information they gave you, but other than Faraday's constant, everything you needed was in the balanced redox reaction. So we just put it back into half reactions and got out of it what we needed. Okay. So that is that type of problem. And that, again, is related to relating Faraday's constant with cell potential and Gibbs free energy. Anytime the question is Gibbs free energy versus E cell, this is your equation. All right, another equation called the Nernst equation. The Nernst equation really is calculating cell potential. So you see this E, but notice it does not have a degree on it. Okay, so this is taking the standard cell potential and figuring out what the cell potential will be under non-standard conditions. Okay, so this is non-standard. This is how we figure out if we're not 1 molar and 25 degrees Celsius. So if we take a look at the equation, the non-standard cell potential will be taking the standard and subtracting from it 2.303, so that's always that way, times R, and this is the 8.314 version of R, okay, and the unit on that is joules per mole Kelvin. The reason why it's 8.314 and not 0.08206 is that this has to do with energy, okay, remember 0.08206 has to do with gases. Then our temperature, which of course needs to be in Kelvin, and then our N again is back, remember it's the number of electrons, and then Faraday's constant is the number that we already established it to be. And then over here, you see our friend Q back. Remember, Q was in our reactions that we had. It was the products over the reactants with the coefficients as exponents, because remember, it was a part of the equilibrium chapter, and it was the same thing as equilibrium, but when we're not at standard conditions, or if we weren't sure if we were at equilibrium, we used that Q. Okay, so it's just products over reactants. You can see it right here. Products minus reactants, coefficients as exponents. Okay, so lots of variables, but not too bad once you start plugging them all in. All right, so let's look at an example. Now you can see in this example that we've been given a lot more work than we were given in old problems. Okay, so, or in the last problem. Definitely some more information has to be supplied. So they want us to calculate the EMF at 298, and then they tell you at these concentrations. So you immediately know that this is non-standard because you are not at 1 molar solution. The temperature actually is still standard. Doesn't have to be, but it is still standard, but the concentrations changed. So we're going to set our equation up. First of all, let's write it over here so that we know what we're plugging into. So we have our standard reduction potential minus, and then we'll have 2.303 times R times T over N times F, and then that whole thing is times the log of Q. So we have lots of things to calculate. So let's start with, what do we want to start with? Well, let's start with see what we have, I guess, is the best way to go at it. So we have our standard cell potential, see right here. The standard EMF for this reaction is 0.79. And then we know 2.303, and we know 8.314, and we know the temperature, it's 298. Okay, we don't know N, and we know F. Oh man, I'm going to run out of space. And then log of the concentration of the products over the concentration of the reactants, coefficients as exponents. So let's look those up. So I have 2 chromiums. So right here is the concentration of chromium. So I'm going to do chromium's concentration, and that's going to, I'm totally not going to have enough space, am I? You know what, let's calculate Q over on the other side, just so that I have space. So Q is going to be products over reactants. So we're going to have 2 chromiums, so it's going to be the value, and it will be squared. Okay, remember you just do products over reactants, coefficients as exponents. So it'll be squared. Then we have, that's the only reactant that we have a concentration for, because this is solid and this is liquid. Remember, equilibrium doesn't deal with solids or liquids, just gases and aqueous solutions. Then chromate, dichromate right here has a concentration of 2 and the coefficient's a 1, so its exponent will be a 1. Then we have H+, it has a concentration of 1 and its exponent will be 14 because there are 14 H pluses. And then I has a concentration of 1 and there are 6 of them, so it'll be raised to the 6th. Okay, so take all of that, plug in our calculator carefully, and you should get 0.89 volts. That's wrong. That's our final answer. Sorry. I don't have the intermediate one here. Let's figure out what that is. Okay, so 1e to the -5th squared divided by 2, and then those ones, of course, will just be 1. So Q is going to be 5 times 10 to the -11th. Okay, so we're going to come over here, and I'm actually going to plug that in. So the log of 5 times 10 to the -11th. You can integrate that. That's what I was going to do, but I just ran out of space. That's the only reason. All right, so that is finding Q. Now what else over there are we missing? Looks like the only thing we're missing is N. We just need to know how many electrons were transferred back and forth between these. So if you take a look, this is going to be part of your balanced equation. That's going to be one of them. And then your other half reaction is going to involve iodine. So we have Cr2O7 minus 2, and it's becoming 2Cr plus 3. Sometimes it's hard when you're looking up there to figure out where these guys belong, which half reaction. So I always like to just do them. So if this is what it looked like, then there must have been 7 H2Os on this side. And if there were 7 H2Os on that side, then there were 14 H pluses on this side. So that gives me a plus 12 on the reactant side and a plus 6 on the product side. So that means there are also 6 electrons over here on this side. And then for iodine, they had 6I minus yields 3I2. So nothing else needs to be fixed on that one. But I have a minus 6 on the reactant side, so there must have been 6 electrons on this side. So again, 6. You really only had to do 1, I guess. But 6 electrons is your number. So if we plug all of that in to our calculators, and then I'm just double checking all my numbers. Yep. If we plug all of that in, we should get, whoops, not standard, silly me. Okay, get rid of that. We should get a non-standard cell potential of 0.89 volts. Okay, which is different than the standard because again the concentrations were not the same. All right, questions about that? You can make sure you just email me, but take a good look at it. All right, next one. If we are at equilibrium, okay, if we are at equilibrium, then the cell potential equals 0. Okay, if we are at equilibrium, the cell potential equals 0 because that means electrons are not going to be flowing back and forth. So there is not going to be any voltage if we are at equilibrium. Equilibrium happens in redox reactions kind of in a unique fashion. We're not going to get into it, but this is the part that's really important that you know, okay, that the standard potential, not standard, the cell potential will be 0 at equilibrium. If that's the case, if you take the Nernst equation and instead of calling this one E, you call it what it is, which is 0, then you could still use the exact same equation to calculate KEQ. Okay, notice this time this is called KEQ instead of just Q because we are now at equilibrium. So that KEQ might be a KC or a KP or a KA or a KB. KEQ is the general one that means any of them. So the same equation, but now Q is K because we're at equilibrium, and the cell potential is 0 because it's at equilibrium. So if we go to the example problem, you see it says calculate the equilibrium constant. So they're telling you you are at equilibrium. And again, they didn't give us a ton of information on this one, but they gave us plenty. We got everything that we need. Actually, you know what? To be honest with you, there is a missing piece of information, which is the temperature. So for this one, we're still under standard conditions. If they don't give it to you, then you can assume that the temperature is standard. So let's go ahead and plug in. So you know you're going to do this equation. Call it log of K now. And you know, I really should have just right off the bat made this a 0 because we are at equilibrium according to the problem. If we plug in what we know, so we know 0, we know the cell potential. Ooh, we don't know the cell potential, so we're gonna have to figure that guy out. I thought it was given, but no worries, I can come up with that. So we need the cell potential, standard cell potential. We have the 2.303, we know R. We know T. We don't know N yet. We know F. And we are solving for this guy. That is our variable that we're going to solve for. So I need the standard cell potential, and I need N, which means I need to dissect my balanced equation back into its half reactions to figure out what it's going to be. So if we look at our balanced equation, we have, I always like to start with the non-oxygen hydrogen ones. So I have 4Fe plus 2 becoming 4Fe plus 3. Okay, so balanced charging wise, I have a plus 8 over here, and over here I have a plus 12, which means I need 4 electrons on that side. That tells me right off the bat how many electrons there are, to be honest with you, because that had to have equalized when they had balanced this. But we do need the other side so that we can figure out the cell potential. So we have O2 plus 4H plus yields 2H2O. And there must have been 4 electrons on this side, which we anticipated. You know, let's go right back up and just plug in 4. So we now know that. And then we look up our potentials for these ones. So this reduction potential standard for this one is 0.77. And the reduction potential for this one is, oh boy, it got cut off, 1.23. Okay. And we know that E cell, standard cell potential, is going to be the one reduced minus the one oxidized. So when we do that, we get a difference of 0.46 volts. So now that we have that 0.46, come back up here, plug in 0.46, and now it's a matter of some math. So here's what I'm going to do to show you the math. There's multiple ways to do this, but I'm going to start by subtracting over the 0.46 to this side, okay, so that I can get all of that mess over there by itself. When I do 2.303 times 8.314 times 298 divided by 4 divided by 96,500, I get negative 0.014782 times the log of K. Then I'm going to divide over the negative 0.014 number, and when you do that, you get that the log of K is equal to 31.119, and then you're going to hit second, and then your log button, that'll give you the inverse of log, and then you're going to put in 31.119, and your K value will come out to be 1.32 times 10 to the 31st, I believe, although I'm having a hard time reading my work, so I'm going to double check. Yep, 1.32 times 10 to the 31st is your value of K. So that is it. We will practice some of these problems tomorrow, but I really want you to make sure that you understand all your variables, that you understand how to take that half reaction and pull it apart, and to figure out cell potential from it, and to figure out the value of it. Okay, so if you need to, go back and rewatch the video, please. Homework, an email. All I want you to send me in the email is any questions you have. If you have no questions, simply send me a smiley face. Okay, we'll make it nice and quick for you tonight. All right, I will see you guys tomorrow.